In this session, we're going to talk about evaluation in Spark, and in particular, reasons why Spark is very unlike Scala collections. So, as I've already pointed out in previous sessions, there's this laziness, eagerness thing going on between transformations and actions. We covered some simple examples which showed how evaluation was different in Spark. These differences can compound and lead to inefficient programs. So it's very important to understand completely how your Spark programs are being evaluated, because there are many situations where you want to avoid unnecessary evaluation in Spark. So in this session, we're going to look at exactly how evaluation works and some common scenarios that you should think about when writing Spark programs. So let's first start with a little bit of a digression. So why is Spark good for data science? In order to answer that question, let's start by recapping some major themes from previous sessions. So in the last session, we learned about the difference between transformations and actions, in particular that transformations are deferred or lazy, and actions are eager. They kick off stage transformations. So we learned that last session, and a few sessions earlier, we learned that latency is important. It makes a big difference in the experience of the actual data analyst using Spark, and that if we can shift things in memory as much as possible, we can significantly lower these latencies and save a lot of time and improve the experience of the analyst analyzing data. This analyst can get more work done, basically, with lower latencies. There are these 2 points that we've learned in previous sessions, and somehow they're going to come together into an answer about why Spark is good for data science. Can you see why? Is it clear yet? I'll give you a quick hint. Most data science problems, when you think about them, they involve some kind of iteration. So how do transformations, actions, and in-memory computation, how are these things somehow important to data science problems that involve iteration? Well, first, let's look at iteration and Hadoop. So here's a graphical illustration trying to show what an iterative program would look like, a program with, at least 3 iterations, probably more. In this example, what we have is some kind of input, perhaps some data in HDFS. And then we have iterations that are implemented as little MapReduce programs, and we iterate by running these individual MapReduce programs many, many times. So at each iteration, we probably have a map and a reduce step. And between iterations, we want to write the data that we computed, and then we want to read it again for the next iteration. So we know that there's probably reading and writing going on in each of these iterations. And there's also reading and writing going on between these iterations. So we have to read and write this intermediate data each time we want to end or start a new iteration. So one thing that might jump out at you, if you recall the latency lecture, is that a lot of time is spent then in I/O, disk I/O, or even network I/O. One figure has attributed around 90% of this time being spent in I/O operations, which Spark can avoid. So if you want to do iteration in Spark, it can be much more performant because all of this reading and writing to disk can be completely avoided in Spark. We have to, of course, read in data from HDFS, but once things are in memory, we can just iterate on it in memory. We can run the same sort of MapReduce steps or filter or whatever steps many times again and again and again for however many iterations that we want, and it's all sitting in memory. It can still be recovered if there is a failure, and there's a lot of reading and writing and things that just don't have to happen because we don't need to persist things to disk all the time. So to begin to answer this question about why Spark is good for data science applications and why transformations and actions and in-memory computations are important, we can start to see here that it's better for iterative programs to be done in memory because they'll be faster. But what does it have to do with transformations and actions? To understand why transformations or actions have to be carefully thought about in this situation, let's look at a quick example. So let's look at logistic regression, which is kind of the hello world of big data iterative algorithms. Logistic regression is a popular iterative algorithm that's typically used for classification tasks. So assuming you have 2 different classes of data, blue and red, and what we want to do is we want to come up with a classifier, a way to separate out these 2 different classes of data. So the classifier would be basically this line. We would move it around on this space here, until it separates these two classes of data, and then if we ever get new data, we assume that it follows the same trends as the red and the blue, and hopefully it should work for any new data that's added, right? That's the idea of a classifier. So just visually, to get an idea of what we're doing here, on one iteration, we move the line a little bit. On another iteration, we move the line a little bit. We keep doing this. And like I said, we're iterating through all of the data every time. We're doing some math with all of the data. And then eventually, we find a good separating line here, and the algorithm stops. What we're focused on is less the details of logistic regression, but we're really focused on the shape of the computation, the fact that we pass through all of the data on many iterations to come up with a new estimation for this line separating the two sets of data. That's the shape of the computation that we're going to be looking at. And this is how we're going to update those weights that represent the position of that line that separates the two classes of data, right? So as you can see here, there's a number of iterations that we're going to do, and we're going to iterate through this XY data set. And there's some function g, which doesn't need to be shown here, but it's part of the logistic regression algorithm. So this algorithm can be implemented in a very straightforward way in Spark. Here it is. So just to step through it, what we have here is first we have an RDD, points, and this is read in from some text file somewhere. And then this text file is parsed, so we have a map function that goes through all of the lines of this text file. Remember, text file gives you an RDD full of strings, so we have to convert all of these strings into most likely doubles here. We have a vector of weights, so these W's here, which we initialize as 0. And then for some number of iterations that we determine elsewhere, we go through the entire data set several times. So here we go through all of the points, and then we apply this g function here, okay? And then we reduce, and now we update the vector of weights here, using what we have just computed, using this gradient that we just computed. Okay? Okay, cool. So now we understand the basic shape of this algorithm. It's pretty concise, isn't it? Essentially, we iterate on applying a map and a reduce. For some number of times, on a certain RDD, we apply map and then reduce. So we do this perhaps 30 times. And you update some local vector with the results every single time you go through this entire data set. Okay, so that's the general shape of this algorithm, but what's really happening here? Remember on the first slide, we were talking about trying to keep computations in memory and having to think about what are transformations and what are actions. So what's really going on here? I'll give you a second to think about it, and then we'll talk about it on the next slide. Well, the short answer is that we're doing a lot of work that we don't have to do. Remember, transformations like map get reevaluated every time an action is used. So we do have one map here, which gets reevaluated when we call this reduce here, but we also have a map here. That means we're applying this map function again and again and again when we don't have to. So points is being reevaluated on every iteration. If we have 30 iterations, we're reevaluating points 30 times. That's completely unnecessary. We shouldn't have to do that. That's a lot of extra work that we don't want to be doing right now. It would be much better if what we could do is create this points RDD, leave it sitting in memory because we know that's faster, and then reuse it on every iteration. Instead, what we're doing is we're recomputing it on every iteration, which is surely very expensive. So we see here a major consequence of these lazy semantics of these transformation operations. By default, RDDs are recomputed each time you run an action on them. That's something you can't forget about. And of course, as we just saw, especially in the case of an iterative algorithm, this can be very expensive in time if you need to use the data set again and again. But what's nice about Spark is that it gives you a way to control what data you have cached, sitting in memory, available to reuse again. And in order to instruct Spark, hey, I'm actually going to use this again, don't recompute it 1,000 times, you can use a method persist or a method cache. What these methods do is after an RDD is evaluated, it keeps them in memory so you can reuse them again. So here's a quick example of a situation where you might want to use this cached function or this persist function. So recall this example where we have an RDD full of strings that represent a year's worth of logs. And let's just say we want to go through all of these logs and we want to filter out the ones that are actually errors, right? And we know we're going to have to use this a few times. So here we have an action take. And in this case, so far, if we didn't use persist, this would be okay. What we would be doing is we would be evaluating it once at the point which we call take 10, and that would be it. We wouldn't need to evaluate filter a bunch of times because we only really use it once. However, if I add a line of code here, here's another action, so I have now take and count. It's beneficial now to persist this logs with error RDD, because if we don't persist this, if this is not cached in memory, then what happens is I do this filter on last year's logs twice. I do it when I compute take 10, and I do it when I compute count. So what we can do is, if we do persist, that means that this logs with errors, this RDD sits in memory, and it can be reused. So it can be, we just use that again without having to recompute this filter for the take 10, and then we again reuse the same RDD that's sitting in memory to compute this count without having to go through that filter again. So if we go back to this logistic regression example that we just saw, we can add persist to this points method here, and what that'll do is that'll prevent us from having to evaluate it on every iteration. Now we just evaluate it once, and then we reuse that data set that's sitting in memory each time we do this map and this reduce on this points data set to compute this gradient on each iteration. So here we can save a lot of effort and not have to continually recompute this RDD by caching it in memory the first time we use it. Okay, to delve just a little bit deeper into caching and persistence in Spark, it's possible to persist your data set in many different ways. For example, as just regular Java objects sitting in memory. So just as your program normally runs, nothing special, just keep your data in memory. You can also persist it to disk as regular Java objects. You can persist in memory as serialized Java objects, so that is converting these objects in memory to byte arrays, or arrays of bytes, which is much more compact, but it takes some effort serializing and deserializing, so it saves memory, but it costs a little bit of compute time. Same thing, put these on disk, or a mixture of keeping data in memory and on disk. And in particular, in this case, rather than reevaluating many transformations a bunch of times, anything that needs to spill over to disk, in case you don't have enough memory, everything that you can keep in memory, you keep in memory, but if you don't have enough memory, then we persist the thing that you tried to cache to disk. That's actually very different from this here. If you run out of memory, in this case, you don't have enough memory between all of your nodes to hold the data set in memory, what happens is a least recently used policy for evacuating things out of memory. So let's say you have an RDD, let's say you've done 20 transformations on this, and it takes a long time to go through all of them, right? If you don't have enough memory to hold that resulting data set, if you call persist on it, and you've chosen this mode here, what happens is Spark only holds as much as it can in memory, and anything else that it can't hold in memory, it throws it out. If ever those pieces of data need to be reused, then it will reevaluate them. It will go through all of those many transformations that are required to reevaluate the missing pieces of data it doesn't have. So in this case, this right here could be very useful in a situation where it takes a lot of work to get to whatever thing you try to persist, and then can persist at least the thing that you've already computed. So just to give some context, there's many different ways you can configure actually how persistence works in your Spark job. And the two methods that you use are cache or persist. Cache is the shorthand for the default storage level. So storage level is what we use to configure these things. But you can just write cache with some parentheses behind it. And that will be the default storage level, which is memory only for regular Java objects. That's this one here. And persist is another method that you can pass different arguments to, representing one of these so-called storage levels in order to customize how the persistence works. So this is the method you use if you want to change the default behavior. And just to show you a quick chart of the different storage levels that are available, these are the things that you pass to that persist method, and here's just a chart kind of showing the pros and cons of different storage levels. So for example, memory only uses a lot of space, but it's pretty fast because you don't have to do any extra processing on this data. It's always in memory, never on disk. Whereas some of these other ones, like memory and disk serialized and whatnot, again, they have different trade-offs, right? So when you keep things serialized, it costs a bunch of time to serialize and deserialize it, CPU time. But of course, it uses very little space in memory. So you can put more data in memory, but of course, you're going to have to serialize and deserialize each individual element of that data set if you want to ever access it. So there are different trade-offs. These is for you to decide depending on the job that you're doing. But just be aware that there are a lot of choices. But in general, throughout this course, we're always really just going to use the default. So we're going to use this memory-only storage level, which you can get by just calling cache or persist without arguments. So a key takeaway of this session is to remember that despite how similar Spark looks to Scala collections, this is deferred semantics of the RDDs that you're using have a very different behavior compared to Scala collections. So the need to use this cache function to prevent things from being evaluated multiple times, for example, this is completely unlike Scala collections, even though the same interface is available to you. And you've got to remember this because this could be the difference between you waiting a really long time for a job to complete or a job being finished in a few seconds. Just to reiterate, due to the lazy semantics of these RDD transformation operators, and due to many users' sort of implicit reflex to assume sort of the eager semantics of regular Scala collections, one of the most common issues that newcomers have when they start using Spark is this issue where people are unknowingly reevaluating several transformations. So you're just kind of doing the same computations again and again and again without realizing that you're doing these many computations again and again and again. And you could save all that effort by doing caching. And of course, this is something important to point out when you do your programming assignments. This is something that students mistakenly do all the time. And as a result, during the programming assignments, lots of students have a tendency to run out of memory and to not know why. This is a big hint. This is probably going to be the main reason why you might be running out of memory in your programming assignments. So just before we conclude, I want to remind you that actually this laziness is really useful. Because after the last slide, you must be like, oh my gosh, I have no idea what's happening under the hood. How do I know if things are being reevaluated all the time? I have to look much more closely than I thought at my Spark programs, which might seem like a bad thing off the top of your head, but I will remind you again, via two examples real quick, why laziness is a good thing. So we saw this example actually in the last session. Just to remind you, let's assume we have an RDD full of strings, which represent a year's worth of logs, and then we do a filter on it to filter out the logs that have errors, and then we just take the first 10 out of those, right? So why is laziness useful here? It's because because filter is delayed until take is applied, that gives Spark the opportunity to inspect this chain of operations that are sort of queued up before being executed. And it lets Spark figure out how to do important optimizations. So, for example, in this case, what Spark can do is it can say, so I only need to find 10 results that match this predicate here from the filter because I'm only going to take 10 of those. So rather than having to go through the entire data set, Spark can intelligently just say, okay, once I've got 10 items that match this predicate here, I'm just going to quit and save a whole bunch of time and not have to iterate through the whole data set just not to use it, right? So Spark can do important optimizations like these. So another important optimization that Spark can do is fusing transformations together. So just like before, Spark now has the opportunity to make an optimization before the count is actually executed. And in this case, what Spark can do is it can stage these computations and then fuse them together, so it has to do less work. So in this case, because map usually requires that you do one entire traversal through a dataset, and filter also requires you to do one entire traversal through a dataset. Spark can say, hey, look, I've got 2 traversals that I've got to do. Maybe I should only traverse this dataset once rather than many times, and I can compute the result of both the map and the filter in a single pass before returning the count. So what Spark can do here is it can basically optimize this, and instead of pass through the dataset many times like would be the case for eager collections like Scala's regular collections, in Scala's regular collections we would be passing through the dataset many times. Spark can very intelligently say, I don't have to do that, I can do less work. So laziness, remember, it's a very good thing. You just got to remember that you have to think about it when you are writing programs. You can't just write code and imagine that everything is eager. You have to remember that transformations are lazy.